All right, this is video 2 for the sound unit notes. In this one, we're going to start talking about forced vibrations and resonance. A forced vibration occurs when energy from one oscillating system is transferred to another system. And this one, it's kind of hard to talk about, so I'll have some class demonstrations, but essentially, if you might imagine this, well, this is a fun trick I do with my saxophone. I'll hold down the resonating pedal on a piano. I will play a note in my saxophone, and when I stop playing, I'll hear the same note coming from the piano. And that's because the sound from my saxophone carries its energy through the air, and then when it encounters something else that can resonate at that same frequency, it causes that other thing to start resonating. And this is a forced vibration. Sometimes we also call this sympathetic vibrations, when energy from a vibrating system is transferred through the air and causes another system to vibrate at the same frequency. So some examples of these, first off is your eardrum. When you hear sound, what's happening is the sound is traveling through the air as a wave, and when that sound hits your eardrum, it causes your eardrum to vibrate at the same frequency as the sound waves. Inside your ear, there are little tiny hairs, and each hair will vibrate at a certain frequency. So when sound, which is composed of many different frequencies, enters your ear, causing your eardrum to vibrate, each hair will vibrate at a certain frequency. That is then converted into electrical signals, which is sent to the brain and processed by the brain. So each hair has something called a natural frequency. And this is the frequency that an object will vibrate at when hit or struck. And this also goes back to sympathetic vibrations. Objects will only vibrate at their natural frequency. So when there's sound waves traveling through the air, if there's something that has a natural frequency that's the same frequency as that sound wave, it will begin to vibrate at that frequency. Tuning forks are a great example of this. Tuning forks each are tuned to vibrate at one single frequency, their natural frequency. Now this leads us to something called resonance. This is a condition. It exists when the frequency of a force applied to a system matches the natural frequency. The object will begin to vibrate at its natural frequency. And if you continue to give that energy at the same frequency, the object will begin to vibrate more and more violently. So when an object resonates, it's vibrating at its natural frequency. And if it continues to receive that energy, its amplitude increases more and more and more and more. And this could potentially cause the object to explode. So think of the opera singer singing at a glass. Some examples of resonance: if you were to run your finger around the rim of a wine glass, you can create a sound. Another example is if a person is swinging on a playground in a swing. What they do is they match the frequency of the swing, which is really just a big pendulum. And when you match the frequency, you can resonate, which causes you to get a larger and larger amplitude. So that's how you can, make the swing go farther and farther. All right. Now for some review. Uh, we've talked about this before, wave interference. Remember that when a wave hits a fixed boundary, such as this example right here, it will reflect on it will invert the amplitude. And if the wave hits a loose boundary, it will reflect without inverting. When waves collide, they pass through each other. They carry energy, not matter. So when the peaks overlap, we get constructive interference. When the troughs overlap, we get constructive interference. I need to change this. When the troughs and a peak overlap. So when a trough and peak overlap, we get destructive interference. And with this, with the math, you just add or subtract the amplitudes. When we have two sound waves traveling at the same amplitude, the same speed, but slightly different frequencies, we get regions of constructive and destructive interference, which creates a phenomenon called beats. And you know, musicians, we listen to these beats when we're trying to figure out if we're out of tune with each other. And the math for this, you just subtract those two frequencies. All right, that concludes video 2.